All right, so we are done with this chapter in terms of the equations. I hope you can make sure you completely understood the simple equations that we derived, because now we are going to add uh, various assumptions and look for large scale balances, and even look for ocean circulation, atmospheric circulation, which are remarkably different because the ocean has boundaries and the atmosphere doesn't, and so on and so forth. But there are many similarities as well in terms of the large scale balances. But first we need to make sure we understood that the Coriolis does vary from the equator to the poles. So if you look at the F, the local Coriolis 2 omega sine phi, at the equator phi is 0, so obviously F is 0. And you can see that it increases with latitude at 10 degrees 0.25, almost 3 times at 30, almost 4 times at 45, and so on. So it's not a linear increase. Okay, so there is a non-linear increase. So 10 times 9 is 90 degrees, but 0.25 times 9 is not what you would get here. And remember, the units is 10 to the it's a frequency, so 10 to the minus 4 per second. Okay, and beta, which we'll see turns out to be a very critical player in the ocean atmosphere flows as well, is the gradient. So we said it's changing with latitude, which means there is a df dy. In this case, we are writing small d, small df, small dy. Why? Because f here is only a function of y. Some people use this for a substantial derivative as well, but that can be confusing. So it's better left, this d is better left to functions that are of only one variable, in which case d dy, you don't need to write partial f partial y, right? So it's just df dy, which is 2 omega over a cosine phi, obviously also non-linear. This is now in 10 to the minus 11 per second per meter, because y, latitude, is in meters, right? So you can see that beta is largest at the equator and drops off to 0 obviously at the pole, because that's the end of the Coriolis variation. And this matters as well. The beta effects, as we will see, as we will learn what they are, matter especially for the ocean. The latitudinal variation of F turns out to be very important. A couple of historical characters who have played a big role in the equations we looked at. Leonhard Euler, obviously you would have heard his name in so many different contexts. Made many contributions to mathematics in analytic geometry, trigonometry, calculus, number theory, and so on. So he published major works in the 1750s, which gave us many of the equations for fluid mechanics, continuity equation, Euler's equation of motion in an inviscid, incompressible fluid, and so on. So we used it to say Eulerian derivative versus Lagrangian derivative, right? Fixed point versus moving with the parcel. Gustave Gaspard Coriolis is a French mathematician who officially formulated the Coriolis force. Remember that Hadley had figured out in 1735 that trade winds were affected by the Earth's rotation, but he didn't figure out this deviation to the right, etc., etc. He had intuitions about why they produced the easterlies and the westerlies, but nonetheless Coriolis gets the credit for doing it rigorously. This is our lab setup that we looked at with the drain in the middle. So you would set up solid body rotation or pump water in at the edge and give it angular momentum, and then see how the things evolved as they headed towards the drain in the middle, and we had said that the amplification was happening because the radius decreases as the fluid parcel moves from the outer edge to the drain. Similar amplification happens on Earth as well, because as you go from the equator towards the poles and the latitudes increase, the distance from the rotational axis decreases, so you still get this you get similar effect of R1 at the equator divided by R0 at some latitude in terms of the local omega sine phi, which is our F, right? So the sphere also has this amplification effect created by here it's created by moving towards the center and reducing R, whereas here it's created by moving towards the poles and reducing the R, the distance from the local distance from the axis of rotation, which we saw before, right? So just make sure you understood the thin shell approximation, the rotational effects, modified gravity, reference ellipsoid to forget about the bulge in the Earth and come back to the sphere, and the modified measured gravity, with the additional complication being the latitudinal variation of F, or the beta effect. Okay, just to reaffirm what we said in the very beginning, as if you just let's say you took this fluid and dropped some dye into it, if there is no rotation, no stirring and so on, the diffusion will happen and the fluid will just diffuse and form because of molecular motions, Brownian motions. You get slow diffusion based on gradients of the dye, whereas if you have rotation, then you are going to get these beautiful swirls. The entire universe is rotating, so if you look at the Hubble telescope pictures and so on, you will see these kind of swirly motions in the nebular dust and the arrangement of the Milky Way galaxy, stars and planets along these arms of these spirals and so on and so forth. So we will see that the rigidity of the fluid parallel to the axis of rotation also ends up creating additional two-dimensional turbulence and so on, concepts that are very exotic and give very exotic balances of forces, unlike the non-rotating framework we are used to at small scales. When you do fluid motion in pipes and so on, or even around an aircraft, etc., we don't worry about rotational effects, right? We worry about laminar flow, turbulent flow, low Reynolds number, high Reynolds number, and so on. We'll end up with different non-dimensional numbers in rotating frameworks, which generate very different, very beautiful solutions and instabilities as well. Lovely chapter. Equations, derivations, make sure you understood the equations at least and can walk through the derivations with the book, even if you don't want to remember all of them. Concepts are easy, important, and must be learned.